So we have, from the previous session, we have learned that the at the resonance, yeah, where the voltage gain, when we measure the voltage gain at the resistor, yeah, at the load, basically, and compare the ratio with the voltage source, what we have is like this, yeah, at the zero frequency, sorry, resonant frequency, it has the maximum amplitude, but then at lower frequency, then it starts to decrease. After that, at higher frequency, it has also decreased. And the bandwidth is defined as the width between the lower frequency and higher frequency, where the relative magnitude is 1 over square root of 2, coming from this formula. And then, so from here, then the bandwidth is obtained when the bandwidth is defined as omega 0, divided by the quality factor. And the lower frequency limit part is equals to omega 0 multiplied to minus 1 over 2q plus square root of 1 over 2q squared plus 1. Okay, now we are going to study the q factor itself. Yeah? We have learned about the formula of quality factor, yeah, which is equal to omega 0 L divided by R, or equal to 1 over omega 0 CR. Yeah, basically, it is the ratio between the reactance at each of the passive component compared to the resistance. Yeah, omega at inductance can be measured by the ratio of the reactance at the inductance omega 0 L to the resistance, or the reactance at the capacitance, which is 1 over omega 0 C divided by the resistance. And from the theory of RLC, we know that resistor dissipate the energy. Any current flowing through the resistor, its energy will be dissipated as heat. Yeah. While at capacitance, it stores energy in the form of electric field. And in the inductance, the energy is stored in the form of magnetic field, and which you will learn this electromagnetic in semester 4, okay, with Pak Fatoni. Okay, because it is quite important that you understand electromagnetic field, because its application is not only in the electric network, but also later in other instrumentation like magnetic resonance imaging, and CT scan, etc., etc. With so from this formula, we know that for series circuit, the high quality factor can be obtained when the R, the resistor, is low. Yeah, when the value of the resistance is small, then the quality can be increased. For parallel circuit, on the other hand, high Q can be obtained when the resistor is high, resistor has high value or low conductance. With high quality factor, we will have small bandwidth, as explained in the previous slide. When quality factor is very high, we have very small bandwidth, or we call it very sharp bandwidth. So like this, when this is Q, when we have Q1 here larger than Q, then we have sharper bandwidth. Also, the energy is still the same. The energy is the same, only then it will have a higher magnitude at omega 0. When we have Q2, which has value lower than Q, then we have a wider bandwidth. Yeah, then the magnitude at the omega 0 will be also smaller. So Q can also be interpreted from energy point of view. Yeah, as we know that Q equals to the 2 pi times the maximum energy stored divided by, this is another definition of one quality factor, the maximum energy stored divided by energy dissipated per cycle, yeah, times the 2 2 pi factor. So basically then we know that the energy stored is at capacitance and inductance, when energy dissipated is at the resistor. So the dissipated energy equals to the Ri squared, R effective here, I effective current squared, multiplied to omega 0 divided by 2 pi, or equals to 1 over 2 Ri squared times omega 0 divided by 2 pi. This is now maximum, not effective anymore, but maximum current squared. So the stored energy, on the other hand, is at the C or at the L, equals to, this is from the inductance law and this is from capacitance law. From inductance law, you know that the stored energy at the inductor equals to 1/2 of Li maximum squared, equal to half C times voltage maximum squared. So the WS, the maximum energy stored divided the maximum energy dissipated per cycle, equals to, so this divided by this. Then the I squared factor cancel each other, and we are left with L omega 0 divided by the half also cancel each other. So L, this Li squared maximum divided by Ri squared maximum. Okay, L omega 0 divided by 2 pi, the 2 pi factor from this dissipated energy, divided by 2 pi times R. Okay, or if we go to, then we know that L omega 0 divided by R equals to quality. This can be also expressed as quality divided by 2 times pi. Okay. Okay. From here, the capacitor and inductor exchange stored energy. Sometimes it is stored as electric field, sometimes it is stored as magnetic field. When one is at maximum, the other one is at 0, depending on the condition. Then energy transfer in resonant circuit. The current here flowing through the circuit is the V maximum, cosine omega t. This is expressed as sinusoidal function divided by the R. This is at resonant, of course. So the components of the impedance at due to L and C are 0. So the voltage at the capacitor equal to 1 over J omega 0 C times I. This is equals to the V maximum here divided by R at phase angle 0 divided by the impedance at C, which is 1 over this is the current, times the impedance at 1 over J omega 0 C. This equals to Vm divided by omega 0 RC. This is the magnitude, and the phase angle is negative 90 degrees because of this. Over 1 over J equals to minus J. Minus J is negative 90 degrees. Then the voltage at C here, at the VCT here equals to the Vm over omega 0 RC. From here, cosine omega, this is expressed now as the sinusoidal function. It's cosine omega 0 t, the omega 0, the resonance frequency, negative 90 degrees phase angle, equals to, and we know omega 0 t minus 90 degree basically is sine omega 0 t. Pm divided by omega 0 RC, sine omega 0 t volts. Then the power, the energy stored at the capacitance, WCT, equals to half CV square T, from the capacitance law. So equals to half C times this value, Pm over omega 0 RC, C sine omega 0 T being squared. Or then equals to Vm square over 2 omega 0 square R square. This is C square times C. So cancel, and then become 1 over C. sine square omega 0 t joules. At the inductance, on the other hand, the energy stored at the inductance is half L I square t. This is from inductance law, equals to half times L. The current is equals to we insert from this value Pm divided by R cosine omega 0 t square equals to Vm square L divided by 2R square cosine square omega 0 t joules. So the stored energy, total stored energy is WL plus WCT here. So the same factor here is Vm square, yeah, Vm square divided by 2R square. Okay, so this plus this plus this equals to Vm square divided by 2R square, and cosine plus multiply to cosine square omega 0 t plus sine square omega 0 t. And the Vm square L here divided by 2R square. Okay, this plus this, yeah. Okay, so and this is the normalization factor. So see here that from the previous slide we have learned that when one in maximum, when the energy stored in the capacitor is maximum, then energy stored at the inductor will be 0. And vice versa, when the energy stored at the inductor is maximum, then the energy stored at the capacitor is 0. Something like that. Okay, so we like from this value. Okay, when omega 0 is, let's say, 90 degrees, omega 0 t is 90 degrees, cosine 90 degree equals to 0. But sine 90 degrees equals to 1, right, maximum. So that's why they are they have reverse values. Let's take the theories into some examples and try to solve some examples. Determine the resonant frequency at this circuit when the also the quality factor Q and the bandwidth when the resistance is 2 ohm here, and when the resistance is 2 ohm, and also when the resistor is 0.2 ohm. The C is 5 microfarad. The inductance is 2 millihenry. So omega 0 from the formula equals to 1 over square root of LC. So we insert the LC 2 millihenry times 5 microfarad. We obtain 10 to the power of 4 radian per second. Then from the formula of quality factor equals to omega 0 L divided by R, or 1 over omega 0 C divided by R. So when the R is 2, when the R is 2 ohm, then the quality factor is 10. When the resistor is 0.2, the quality factor is 100, as we have learned from the previous slide. In series circuit, when the resistor is lower, then the quality factor gets higher. The bandwidth is calculated as omega 0, the resonance frequency, divided by the quality factor. So when the resistor is 2 ohm, quality factor is 10, the bandwidth is 10 to the power of 4 radian per second divided by 10 equals to 1000 radian per second. When the R is 0.2, quality factor is 100, then the bandwidth is 10,000 divided by 100 equals to 100 radian per second. So we see here, when the resistor is smaller, quality factor gets higher and the bandwidth becomes smaller. Yeah, it means that it becomes sharper bandwidth. So the quality factor here equals to 10,000 times 0.002. This is this one, omega 0 times the inductance divided by R. Okay, and the bandwidth here is from this omega 0, this one, 10,000 divided by Q. Another example, a series of RLC circuit with the following properties. When the resistor is 4 ohm, then the omega 0, the resonant frequency is 4000 radian per second, and the bandwidth is 100 radian per second. Now you are asked to determine the values of L and C, inductance and capacitance. So if the resonance frequency is known and the bandwidth is known, then we can calculate the quality, right? We can calculate the quality factor. And from there, we can, from the quality factor, since the resistor is known, then we can calculate also the inductance value, and we can calculate also the capacitance value. So first, we calculate the quality factor, Q, yeah, from here, from this formula. Given resonant frequency and bandwidth, we determine the Q. After that, we given the R, we can determine the L, we can based on the formula of quality factor. And we know Q, we know R, we can calculate also the capacitance. And that is the steps. So quality factor is defined as the omega 0, the resonance frequency divided by the bandwidth. So 4000 radian per second divided by 100 radian per second, quality factor equals to 40. So inductance from here equals to quality factor times R divided by omega 0. 40 times 4 ohm divided by 4000 radian per second. We obtain 0.040 Henry. Then the capacitance similarly can be calculated from this formula. Yeah, otherwise like this one, it uses the formula of resonant frequency. Okay, because so we don't need to use R. Yeah. Otherwise, we can use the formula from quality factor here, as you like, which one you would like to obtain, but we should obtain the same value of 1.56 microfarad. Another example, we have a series RLC circuit. Now we want to operate it as a band pass filter. Okay, I believe you have also done band pass filter in the module 4, yeah, of electrical circuit lab. Now the center frequency is 1000 radian per second. It means the center frequency becomes the resonance frequency. The bandwidth is 100 radian per second. Okay, so from the two information here, you can calculate the quality factor, right? The Q you can calculate. You have the Q, you have the omega 0, you have the Q and you have the omega 0, so you can calculate then the RLC. Okay, or in this case, this one uses the formula of gain, yeah? R over Z, function of J, Z is function of J omega. Omega 0 is 1 over square root of LC. Q is omega 0 L divided by R equals to 1 over omega 0 CR. And the bandwidth equals to omega 0 over Q. Okay, bandwidth is known. The omega 0 is known. Then we can calculate the Q. Okay. If we have Q, then we can calculate L over R. We can calculate also 1 over CR. So this will be the dependent function. The strategy now, determine the Q first. Use the value of the resonant frequency, yeah, omega 0 and Q, to set up two equations with the three unknown. The two equation is this one and this one. Assign a value to one of the unknown, and then some arbitrary value to one of the unknowns. Then the two other unknowns can be calculated. So from here we obtain the quality factor to be 1000 divided the center frequency 1000 divided by the bandwidth 100 radian per second, 10. The quality factor is 10. By the way, the quality factor is dimensionless, so there is no unit. It does not have any unit. So from here, omega 0 is 1000 radian per second equals to 1 over square root of LC. Okay, 1000 squared or 1 million equals to LC, 1 over LC. So 1 over LC equals to 1 million, 10 to the power of 6. Then quality factor using this formula equals to omega 0 L over R. 10 equals to 1000 L over R. Now let's take the example that C, for example, is 1 microfarad. Then we can calculate L. L will be equals to 1 Henry. From here, then from this 1 Henry, R will be equals to 100 ohm. Okay, so in this case, we only have two equations while the unknowns are three. So this is basically a design problem. In design problem, then one of the unknowns you can pick arbitrarily, maybe from a value of a component that is quite common. Let's say capacitance 1 microfarad is quite common. So from this value, then we can calculate L from the formula of resonant frequency, and we can calculate R from the formula of quality factor. Okay, so now we try to study the properties of resonance circuits, the voltage across the capacitor. From the formula of quality factor at resonance, then we can calculate the voltage here at the capacitance to be equal to the quality factor times the voltage at the resistance. However, this is not the maximum value for the voltage across the capacitor. So if we derive further, so the V output here equals to 1 over j omega c divided by the Vs here equals to R, and the ratio equals to R plus j omega L plus 1 over j omega c. If we then multiply both upper and lower parts with j omega c, with j omega c, so this become 1, this become j omega c R, this part, this become 1, and j omega c times j omega L equals to negative omega square LC. Okay, then from the formula of resonance frequency, omega 0 equals to 1 over square root of LC, and the quality factor equals to omega 0 L over R equals to 1 over omega 0 CR. So we define a variable U equals to the ratio between the frequency to the resonant frequency, omega over omega 0. And the gain G equals to the V output over the Vs square. So G as a function of U, so basically this one is this part, this formula, but the being squared. Okay, if we then we squared this formula, so this becomes 1 over 1 minus U squared. So this become omega over omega 0 squared plus U over Q squared. Okay. And the derivative of G over U, which is the gradient, when this is maximum, it means where we want to find the maximum voltage across this capacitor as a function of frequency. Okay, and so we obtain U here is a new parameter which contain the frequency, and we convert this formula into this. Okay, and then we derive it. This is the gain. We want this to be maximum. Okay? We want the V output to be maximum. And from calculus, we know the maximum value is obtained when the gradient is 0. So the gradient of G relative over U, which is contained the frequency here, should be 0. And I will not go to the detail of this derivation. You may try at home. So this become 2 times 1 minus U square times minus 2U plus 2U over Q times 1 over Q divided by this square. This comes from the calculus formula. The formula for U over V, U dash V plus V dash U divided by V squared. Remember the derivation formula. So when this equals to 0, we know that this plus this should be equal to 0. The upper part should be equal to 0, or which means that 2 times 1 minus U squared equals to 1 over q square. Yeah. And it means the u maximum, the omega over omega 0 maximum, is obtained, yeah, omega maximum, when omega maximum means the frequency when the voltage across the capacitance is at maximum value, equals to square root of 1 minus 1 over 2q square, 1 minus 1 over 2q square. Okay, so the G max, then the gain maximum will be equals to the put this u value into this formula, so we obtain 1 over 4 q power 4 plus 1 over q square minus 1 over 2q4, or simplified, it becomes q square divided by 1 minus 1 over 4q square. Okay, V output then, since the G is basically here, the ratio between the V output over V source squared, the V output equals to Q times magnitude of Us divided by square root of 1 minus 1 over 4Q squared. Okay. So in this slide, the detailed derivation is not given. Please derive your own. Yeah. This is the result. So just use this result. Now, an example here is given. Determine omega 0 resonance frequency, yeah, and the maximum frequency, maximum radian frequency when at the cross this capacitance, when R equals to 50 ohm and when R is equals to 1 ohm. So natural frequency depends on L and C. The resonant frequency, however, depends on the Q. Okay. So omega 0 equals to 1 over square root of LC, and the Q equals to, the quality factor equals to omega 0 L over R equals to 1 over omega 0 CR. The U max, which is defined as omega max, yeah, the resonant frequency, means that the maximum frequency where the V output across this capacitance is the highest. Omega max divided by omega 0 equals to 1 square root 1 over 1 minus 1 over 2q square, yeah, from here, from this formula. Okay, square root of 1 minus 1 over 2q square. So we calculate first the resonant, the natural frequency or resonance frequency, 1 over square root of LC. We obtain 2000 radian per second. Then we can calculate Q. Q equals to 2000 radian per second times 50 millihenry divided by R. So then the omega max will be here equals to omega 0, which is 2000 radian per second, times this factor, okay, 1 minus 1 over 2q square. When R equals to, using Excel, when R using 50 ohm is 50 ohm, then we obtain Q to be 2. Yeah. When R is 1 ohm, the Q is higher, becomes 100. The frequency, resonant frequency, yeah, where V out is the highest from this, then when resistance is 50 ohm, the omega max is 1871 radian per second. When resistor is 1 ohm, the omega max is 2000 radian per second. Okay. Yeah. So this is using MATLAB when we want to display the frequency response, yeah, as a function of frequency. So we plot it as a function of omega. Okay. And this is at R equals to 50 Hertz. So we know that omega is 2000 radian per second. Omega max is 1887. So this part, yeah. Then the quality factor is low. Okay, the quality factor is low, only 2. That is why here you don't see much high magnitude of the voltage at the capacitance. But when the resistance is 1, quality factor becomes very high, and the resonant frequency here, the omega max, this one becomes very high. Okay, so this is almost equals to 0. That's why omega max approaches to 2000. That's similar to the natural frequency omega 0. Yeah, and with very sharp magnitude. Good selectivity. And we see here the phase angle also, it is completely 0 degree, but at above the resonance frequency, it will just become how many? Minus 180 degrees. Okay, as I mentioned earlier, that resonant frequency as well as the modeling, yeah, of RLC is not only applied for electrical circuit analysis, you can apply it for mechanical system. So this is the example that resonance frequency can also happen in a mechanical system. For example, in this case, this is the bridge system. Yeah, the wind varying. So this bridge is broken, collapsed. Yeah, when several months after its opening. Yeah, after its opening ceremony. Yeah, why is that? Because the design does not calculate the wind. The wind varying at certain frequency, the wind here can be considered as voltage, yeah, applied to the bridge. The bridge system itself can be considered as an electrical circuit having a mass, having a spring, and having a damping system. And all of this can be modeled as a resistor, inductance, or capacitance, respectively. And from there, we can calculate the natural frequency, the omega 0. So when the wind frequency is, and it has very high quality, yeah, when the wind frequency is approaching to the natural frequency, omega 0, what will happen is similar to this. Yeah, when it is omega approaches the natural frequency, then the magnitude of the swing of the vibration of the bridge will become very high. Yeah, so that is why then it breaks, because then the when it vibrates very strong, the strength of the material cannot endure the stress and the strain that is implied on the structure. We will learn about this in next year, yeah, next semester, and the semester following that, the biomaterials as well as in the statics. Okay, so the omega 0 here equals to 2 pi times 0.2. Yeah, the frequency is small, 0.2 hertz. Okay, so this is similar also with our body system. When we receive sometimes stimuli from outside, which may be the same as the frequency, natural frequency to some of our body organ, yeah, it may create some resonance. Yeah, I don't know whether it will be good or not bad. Yeah, depends, yeah, on also how long it is being stimulated. Yeah, like depending, yeah, on which organ, also to the heart, to the lung, or to the intestine. But this is a good example how the resonance frequency analysis, the quality factor analysis, etc., can be also applied to mechanical system. Now, see here, now we are trying to simulate the Tacoma Bridge using electrical circuit. Yeah. So for mechanical system, we model it as electrical circuit. So for example, it is modeled as a voltage in, then as an inductance, as RA, as a capacitance, then this is the load, the RB, the V output, and 1 volt equals to 1 feet. Yeah. At value of 42 mile per hour wind, it will cause 4 inch of 4 feet. Yeah, 4 feet. Yeah, this is 4 feet of deflection. Then the model at resonance, V output divided by V in, yeah, equals to the 4 feet deflection over 42 mile per hour. This equals to RB divided by RA plus RB. So remember, this is at resonance, so the contribution from the reactances are 0. V in at maximum is 42 mile per hour, and the value here RB is 1 ohm, the RA is 9.5 ohm. Assuming a low quality factor of 2.39, and the value of inductance is 20 Henry, capacitance is 31.66 microfarad. So this is what we see here at at 0.05 hertz of frequency. This is the vibration of the wind. So it just creates small swinging. When the frequency at 0.44 feet, when the frequency increased to 0.1 hertz, 0.1 hertz, it is this one, this one. Then swinging increases, corresponding to this 1 point larger magnitude of the output. And finally, when the frequency becomes 0.2 hertz, so the frequency of the wind, so means the wind changes the direction. Then the swing becomes rapidly increases to, actually this is very high, to close to 4 feet deflection, and this caused the collapse of the Tacoma Bridge. Okay. Now we look at the case with parallel RLC resonance circuit. Yeah, the impedance of series RLCs is as we have derived earlier, and we have also derived the admittance of parallel RLC like this. J omega equals to G plus 1 over J omega L plus 1 J omega C. And the series RLC is omega 0 equals to 1 over LC, equality factor equals to omega 0 L divided by R, or 1 over omega 0 CR. The bandwidth is omega 0 divided by the quality factor. In parallel circuit, the current IS will be equals to the total admittance multiplied by the voltage source. Okay, so here IG equals to the conductance times the voltage source. The current at the capacitance equals to the admittance at the capacitance. Yeah, J omega C times the VS, the source voltage, or J omega C divided by the voltage source itself equals to the current S divided by the admittance Y. So the current at the inductance IL equals 1 over the VS divided by the impedance, this L, J omega L, equals to the IS divided by Y times 1 over J omega L. So at resonance, then omega 0 C here equals to 1 over omega 0 L. The Y equals to the conductance. The IG here will be equal to the current source. The IC equals to negative IL. That's why the sum is 0 at the energy storing devices. The IC equals to omega 0 C divided by D multiplied by IS, and IL equals to 1 over omega IL equals to 1 over omega 0 LG times IS. So we notice the equivalence here where the resistance is equivalent to the conductance. Inductance here in the series equivalent to the capacitance in parallel series, and capacitance equals to the inductance capacitance in series is equivalent to the inductance in parallel. The impedance is equivalent to the admittance in parallel, and the voltage is equivalent to the current, and vice versa. So in the parallel RLC, then the omega 0 is still equal to 1 over square root of LC, while the quality factor equals to here omega 0C divided by G. So yeah, instead of R, it is conductance now equals to 1 over omega 0 L times G, the conductance. In parallel RLC, the bandwidth is still the same. Omega equals to omega 0 divided by the quality factor. And it looks similar, yeah, the graph of, but now instead of impedance, it is admittance. As a function omega, it is lowest when at the resonance frequency, where now omega c, and this gradient is omega c minus 1 over omega L. When omega equals omega 0, the Ig, the current at the conductance equals to at the same phase as the voltage source. Yeah. This is then, but the omega less than omega 0, then it is inductive. Okay, it is inductive. While at omega larger than omega 0, it is capacitive. Okay, let's because of time, let's take a break now. Yeah.